Yes, I'll be talking about quantum rate distortion, reverse Shannon theorems, and source channel separation. And this is joint work with Min-Chi Xie, who's also at the University of Cambridge, and Mark Wilday from McGill. So two important pillars of classical information theory are Shannon's source coding theorem, which deals with the compression of information emitted by a source, and Shannon's noisy channel coding theorem, which deals with transmission of information through a noisy channel. So the source coding theorem tells us that if you have a memoryless information source, say characterized by a random variable x with probability mass function p of x, then the fundamental limit on the rate of data compression is given by the Shannon entropy of the source, which we denote by h of x. On the other hand, Shannon's channel coding theorem tells us that if you have a noisy memoryless channel n, and let the input to the channel be denoted by a random variable x and the output by y, then the capacity of the channel, which we denote by c of n, is given in terms of the mutual information of the random variables x and y. Now, typically in a data compression scheme, the signal from the source, let's call it S, is subjected to an encoding map E to yield the compressed signal, and so that it can later be decompressed or decoded to give the decompressed signal, say S prime. Now, if S prime is equal to S, then the data compression scheme is said to be lossless. Now, Shannon's source coding theorem that I talked about corresponds to asymptotically lossless data compression. So what happens here is one considers n copies of the source and say the signal emitted by it is x to the n, and let the final decompressed signal be y to the n. Then one requires that the probability that y to the n is different from x to the n goes to 0 in the asymptotic limit, that is, as n goes to infinity. However, lossless data compression is often too stringent a condition to demand. In particular, for cases of multimedia data, for example, audio, video, and still images, or even when storage space is insufficient. So why is this so? That's because typically a substantial amount of data can be discarded before the information is sufficiently degraded to be noticeable. Let's see a simple example. Let's look at these two pictures of a dog. They look almost identical, don't they? But this is the original image, whereas this is one with 84% of the information discarded. So this brings us to lossy data compression. So lossy data compression is a data compression scheme where the recovered data is not required to be identical to the original data, even in the asymptotic limit. Instead, one requires that the recovered data is a good enough approximation of the original data. So what I mean by that is that one allows for a finite distortion, which we denote by this distortion parameter d. So rate distortion theory, which was part of my title, is the theory of lossy data compression. And it deals with the trade-off between the rate of compression and the allowed distortion. Obviously, if you allow a greater distortion, a larger distortion, you would be able to lower the compression rate. And this theory yields the fundamental limit on the asymptotic rate of data compression for a given maximum distortion d. So let's start with the classical case that was developed by Shannon, and he proved that if you have a given memoryless information source, as I said before, say characterized by a random variable x, and you allow a maximum distortion d, which is a non-negative number, then the minimum rate of data compression, which he called the rate distortion function, and which we denote by our CD, the C denoting classical, he found that it is given by a mutual information. So we know that x is the random variable characterizing the source. So what is y? So y happens to be the output of a stochastic map, Pyx, which maps x to y. So this rate distortion function is given by a minimum of all such mutual informations, where the minimum of this quantity, where the minimum is being taken over all such stochastic maps, such that the average distortion is less than equal to that value d that I mentioned. So here dxy is a distortion measure. This is an example of one. So it's a suitably chosen distortion measure. Okay, two important things to note: that this expression for the classical rate distortion function is less than the Shannon entropy if d is greater than 0, as we would expect, and it becomes equal to the Shannon entropy if d is 0. So if you put the distortion equal to 0, one recovers Shannon's lossless data compression. So what is our aim? Our aim is to obtain rate distortion functions in the quantum realm. And the main motivation behind this is to handle situations in which the storage space is insufficient for lossless data compression. So let's start with the scenario for quantum rate distortion. So for a fixed value of the distortion parameter d, say being between 0 and 1. So the most familiar setting is the storage setting. So say there's Alice, and Alice has a memoryless quantum information source. Say this is characterized by a density matrix rho acting on a Hilbert space HA. So A is the system which is the source. Now she considers the signal emitted by n copies of the source, and she encodes them to get a compressed state. In a Hilbert space, let's call it H and C, where now C stands for compressed. This can be later decoded to give the recovered signal. So for this compression-decompression scheme, the rate of the scheme is said to be R if, roughly speaking, the dimension of this compressed Hilbert space is 2 to the nr. Further, this rate is said to be achievable if the average distortion of the source state rho tensor n under the encoding followed by the decoding is less than equal to d. This is what we denoted by. In the limit n tending to infinity. So in the asymptotic limit, the average distortion is less than equal to d. So as we have a classical rate distortion function, one can define a quantum analog of quantum rate distortion function. It is then defined as the infimum of all such achievable rates. So physically speaking, it just corresponds to the minimum rate of data compression under this given distortion d. And that's what we are after. Right. So in other words, what does the rate distortion function correspond to? We know that there exists some encoding map and some decoding map, such that if Alice compresses the information emitted by n copies of the source into n times RQD qubits, then she would be able to recover it later up to some distortion d. So Q is there for quantum here. So our aim is to find an expression for RQD. So it was Barnum who introduced the field of quantum rate distortion, and he proved a lower bound for RQD in terms of the coherent information. So what is this quantity? So you have the source designated by rho corresponding to the system A, and let psi RA rho be a purification of the source state. So then let omega RB be the state obtained from this purification. R is an inaccessible purifying system. If you allow any possible physical operation, which of course is given by a completely positive trace preserving map, to act on the source. Okay? And the coherent information is nothing else but the negative of the conditional entropy of R given B of this final state. And the lower bound that he proved is a minimum of the coherent information over all such CPTP maps, subject to the fact that the distortion is less than equal to d. And this distortion he defined in terms of the entanglement fidelity. Okay? Now, not only did Barnum prove this lower bound, he also made a conjecture. And his conjecture is that actually that is an equality. The equality holds. Now, however, there is a big problem with this conjecture. That is, as you know, the coherent information sitting on the right-hand side can be negative. And so here we take a minimum over all CPTP maps, so the right-hand side can be a negative quantity. However, the left-hand side is the rate of a data compression scheme, so by its very definition has to be positive. So you see, this is not a meaningful conjecture. Consequently, after Barnum's paper, finding an expression, a valid expression for the quantum rate distortion function had remained an open problem, and this is what we address. So, I defined the quantum rate distortion function in the storage setting. One can equivalently define it in a communication setting. Let's bring in two parties, Alice and Bob. Now, Alice has the source, and she has access to many uses of noiseless qubit channels, which she can use to transmit information emitted by the source to Bob, so that he can recover it up to some distortion d. So obviously, these are equivalent, and the minimum number of such noiseless qubit channels that she would need is n times the quantum rate distortion function. So we will often talk in the communication setting. We will also consider a generalization or an extension where, in addition, we allow Alice and Bob to share some entanglement to assist them in this task. So if we now say that NREAQD is the minimum number of noiseless qubit channels she needs, now in the presence of entanglement, that's why EA, so that Bob can recover the information up to distortion D, then this quantity is called the entanglement-assisted quantum rate distortion function. So now I can set the scene to state our results, and the first result is on the entanglement-assisted quantum rate distortion function. We find a single letter expression for it given by this quantity, which is now the half the quantum mutual information. And the state omega is the one we saw before, that is one obtained from a purification of the source state if you allow a physical operation to act on the source itself. And this is minimized over any possible such CPTP maps subject to the given distortion criterion. So how do we prove such a result? Well, we go about doing it in two steps. First, we prove that this entanglement-assisted quantum rate distortion function is lower bounded by the right-hand side of 2. Now, this is done by using entropic inequalities. I won't go into it. But the interesting thing is that we can also prove that equality holds. So we can prove this bound is achievable. So let me try to give you a brief sketch of this proof. Okay? So we want to prove that that rate is an achievable rate. One way to prove it is as follows. So here is Alice. She has a source, and this is a purification of the source. R is an inaccessible reference. Now let N be the minimizing completely positive trace preserving map of this above expression. And let UN, which takes the source A to systems B and E, be a Steinspring isometry of N. Okay? So Alice has control over the system A, which is the source. So suppose she acts on it locally by this isometry. So what will happen? This pure state will be transformed into this tripartite pure state, where E and B are now with Alice, and R is the reference. Okay, this is the situation, and this is allowed because this is a local map done by Alice. But there is Bob on the other hand, and Alice shares entanglement with Bob and noiseless qubit channels. Okay? So here's the picture for you once again, and this is what we are wanting to prove. We want to prove that that is achievable. Now first note that since this is the Steinspring isometry, that means that if you take the reduced state on the system B, what you get is just the action of the CPTP map acting on rho, right? And because we have chosen the CPTP map to be the minimizing one, this state satisfies the required distortion criterion. So what I'm trying to get across is this state is a good enough approximation of the source state. So if we could somehow transfer this to Bob using the shared entanglement, we would have achieved our goal. So, in other words, it suffices to prove that omega B can be transferred to Bob by Alice through so many uses of the noiseless qubit channel, right? That's what we are asking. How many uses of the noiseless qubit channel do you need? Because we are in a communication setting. So how do we do that? So the question is, how can we transfer omega b to Bob? Bob originally has nothing, and Alice has E and B, and that's the reference. Now that can be done using the protocol of quantum state splitting, studied by these authors. And it says that if Alice sends qubits to Bob at a particular rate, let me now denote it just by Q, and in addition, both Alice and Bob are allowed to do local operations on the systems they possess or receive, then you can achieve your goal. So what is the goal? The goal is that the part B ends up with Bob. So this is called state splitting, because the state which was originally between the reference and Alice has now been split so that Bob has B. And what they prove in quantum state splitting is that this rate is precisely half the quantum mutual information. So that means we need half the quantum mutual information rate. That's the rate at which we need to use these noiseless qubit channels. Okay, one thing to keep in mind is that all this is actually done in the asymptotic setting. That is, Alice works on n copies of the source, and she generates n copies of the state omega BE, and then this state is split with the help of the shared entanglement, so that Bob ends up with omega B tensor n, where omega B is n rho. So this is equivalent to simulating the output of the quantum channel n tensor rho when the input is rho tensor n using shared entanglement. And this again is the special case of another important protocol called channel simulation or quantum reverse Shannon theorem. So in other words, we can say that the achievability of the expression for EAQRD follows from the quantum reverse Shannon theorem. This brings us to our second result, where we forget about entanglement. So this is unassisted quantum rate distortion, and we can look upon it either in the storage setting or in the communication setting, because they're equivalent. And we find that an expression for it is given in terms of the regularized entanglement of purification, which, as the name says, is a regularization of the entanglement of purification, which is defined in the following manner. For any bipartite state, consider such a purification, and a reduced state, oops, sorry, too far. Yeah, and let this be the reduced state on B and B prime, so that the entanglement of purification is defined in the following manner. So you act on the B prime system with any CPTP map and minimize over all CPTP maps. Okay, and this is the von Neumann entropy, this H. So the question is, why does this entanglement of purification arise? Where does it come from? And it comes from, actually, once again, the quantum reverse Shannon theorem, or channel simulation, now in the absence of shared entanglement, because we are in the unassisted setting. So once again, you see, here's Alice. She has n copies of the source. We want Bob to end up with omega B tensor n. And in other words, we are wanting to simulate the output of n tensor n when the input is rho tensor n. And this theorem tells us that if there is no entanglement, the rate at which Alice needs to send qubits to Bob is this expression. Okay, so this is where the regularized entanglement of purification arises. So the full expression is given in the following, but omega RBN is a state obtained in this manner, but I will not go into its details. But I just want to point out that there is a double regularization, which is not a very tractable formula, not a tractable formula, but at least it has the advantage of always being non-negative, unlike Barnum's conjecture. Also, it reduces to the von Neumann entropy when D equal to 0, so one recovers Shannon the Schumacher data compression. Now to our final set of results. I've been talking about sources, but now I talk about sources in conjunction with noisy channel. So you have a source, a memoryless quantum source, and a memoryless quantum channel. Let's ask this simple question. When is it possible to transmit the source reliably over the quantum channel asymptotically? That is, over multiple uses of source and channel. What we prove that such a thing is possible if and only if the von Neumann entropy of the source is less than equal to the quantum capacity of the channel, by which I mean the minimum rate at which qubits can be transmitted reliably of the channel, which is known to be given in terms of the regularized coherent information. We call this a quantum source channel separation theorem because it is a quantum analog of a fundamental theorem in classical information theory called the source channel separation theorem, proved by Shannon, which says that if you have a classical source and a classical channel, and you want to transmit the classical source over the classical channel reliably, you can do it if and only if the Shannon entropy is less than the classical capacity of the channel. Now, this theorem, as like its classical counterpart, has a very important implication. And the implication is that a two-stage encoding is optimal. That what I mean is, in the outer shell, here ES and DS are encoding and decoding map of a source code or a data compression code. And in the inner shell, these are the corresponding maps of a error correction code. So one can design data compression codes and error correction codes separately. Now finally, we can also do this in the entanglement-assisted setting. And we can find here that Alice can reliably communicate the source to Bob if the von Neumann entropy is less than the entanglement-assisted quantum capacity of the channel. But this is the last thing I'm going to say. That is, how does this all connect up with rate distortion theory? It's via this question. What if you're given a source whose von Neumann entropy is greater than the entanglement-assisted quantum capacity? Can you say anything then? What you can say is that Alice can still transmit rho over n up to a distortion d as long as the entanglement-assisted quantum rate distortion function is less than the entanglement-assisted quantum capacity. So to summarize, I've talked about the entanglement-assisted quantum rate distortion function and obtained a single letter formula in terms of the quantum mutual information. For the unassisted case, we found a regularized formula in terms of the entanglement of purification, but which reduces to the data Schumacher compression result for d equal to 0. But most importantly, we have a conjecture that actually it can also be given by a single letter formula identical to that of the entanglement-assisted case. And I'll leave that to the question session, the reason behind it. And finally, we talked about some quantum source channel separation theorems. Thank you.
Thank you. Questions? I would ask to John to set up his talk already while we take questions.
Yep.
Yep.
Okay, so the reason I believe that, sorry, ignore this. The reason I believe the conjecture to be true is because, firstly, note that when you consider d equal to 0, that is when you do Schumacher compression, then the quantum rate distortion function becomes identical in the entanglement-assisted and the unassisted case. So for Schumacher compression, entanglement doesn't help. So that's the first motivation. Secondly, if you look at the classical case, then what you find that if you consider d equal to 0, here the rate distortion function with or without shared randomness are identical. So in somewhat they are analogous results. But also, if you consider d non-zero, you would find that they're still identical. So of course, one said, would this carry on in the quantum case? Well, there is a beautiful symmetry in the quantum case from the point of view of reverse Shannon theorems. What you find is classical reverse Shannon theorem, the symmetries between reverse Shannon theorems and rate distortion functions. Classical reverse Shannon theorem with shared randomness is equal to classical rate distortion function without shared randomness, both being given by the mutual information. And similarly, it would be, therefore, nice to expect that quantum reverse Shannon theorem with entanglement, which we know is given by the quantum mutual information, would be equal to quantum rate distortion function without entanglement. We can prove the converse, so but we're lacking the achievability part.
All right, so you got your extra 3 minutes. Thank you much for the talk.